Great, hello, welcome. My name is John Bird. This is a video on electrical circuits, and we're going to look at some of the formulas associated with Unit 15 of a Level 3 Applied Science BTEC course. And we're going to look at also sort of the graphical relationships between certain quantities and some of the connected with the formulas that we're going to look at. Okay, so let's just swatch my screen over and let's get started. Just while we do that, feel free to, as you're watching the video, pause it, make all notes necessary before you move on to the next section. Okay, so let's have a go. All right, so Unit 15 Electrical Circuits, Section A and B. This will be the first assignment. We're going to look at some of the formulas and we're going to look at some of the graph work. Okay. Okay, so we'll work through the specification just bit by bit. So first formula that we might look at is maybe looking at the relationship between voltage and current and how that affects resistance. We can measure the voltage and the current and how that affects resistance. So we might call this potential difference. This will be current and this will be resistance. We measure potential difference in volts. It's a type of voltage. Current is measured in amps, although you can have milliamps and etc., microamps even. And resistance is in ohms. And the formula that relates these three things together is V equals IR. It comes from the fact that when voltage is proportional to current, we actually call that Ohm's law, provided the external environmental conditions don't change. All right, so that's the formula. If you had to work out I, you divide both sides by R. It cancels on this side. We get V over R. If you had to work out R, then we would divide both sides by I. It would cancel on here, and it would be divided by over here. And so that becomes V over I. All right, Ohm's law. If we plot down a graph, you might see a variety of things. Okay, so if it was for a fixed resistor, then we would expect it to be a straight line through 0, 0, because for a fixed resistor, it obeys Ohm's law. Straight line through 0, 0 means that V is proportional to I. If we were looking at a relationship perhaps for a filament lamp, okay, then although it obeys Ohm's law for low current, as the current gets higher, of course, then the resistance increases, and therefore it sort of curves over a bit. So as the voltage increases, the current doesn't increase by quite so much. So this is a non-ohmic component. It does not obey Ohm's law, a filament lamp component. Whereas a fixed resistor we call an ohmic component. There are other ones out there as well, but for our course we don't need to worry too much about them. All right, and so we might just sneak that in there. So as I increases, R also increases, which leads to this graph. Okay. All right, next. Let's have a look at the next one then. So we can have a look at charge and current. We have a formula Q equals IT. Q is the charge. We measure that in coulombs. We give that the symbol for coulombs, a capital C. I, as before, is current in amps, and T is time, which has to be in seconds. Let's do that better. I'll do that even better, because that's t is time, which is measured in seconds. There we are. It's a bit better, isn't it? Lovely. Okay, we'll have a look at a graph in a moment. If we were given the current and the time in seconds, we just multiply it. Naturally, if we're given the time in minutes, then we have to multiply that by 60 to get it an answer in seconds before we pop it into the formula. Okay, and we can work out how much charge just passed a circuit. All right, so imagine we had a battery, maybe a little bulb, and current would flow around. And again, if we wanted to measure the charge that flowed every second, we'd multiply the current by how long we allow that circuit and the current to flow for, and that tells us the charge in coulombs. Okay, we can rearrange that formula if you want to work out the current. If we're told how much charge flows past a point in a given amount of time, and of course those charge carriers are going to be electrons in this case in a wire. But if we want to work out the current, we divide both sides by T, it cancels on this side, and it comes and is divided over here. So that becomes Q over T. If we wanted to work out how long it takes a certain amount of charge to flow through a bulb, for example, knowing the current, then we divide both sides by I. So Q to cancel on this side gets T on its own, and then it'd be Q over I. Okay, depends on the question, but that's how we'd rearrange those formulas. And this is a context for it. Current flowing in a circuit, we time on a stopwatch maybe how long that current flows for, and we can work out the charge that's passed through that bulb in that time. Okay, something that's a little bit new at level 3. I don't think we certainly don't do this at GCSE, is something called conductance, and we give that the symbol G, and we measure it in the unit is the Siemens, named after a German bloke. We measure it in Siemens, which is given a capital S. So not a little lowercase s for seconds, but it's a capital S for Siemens. All right, and how does that relate to things? Well, we talked about resistance before, and just the conductance is 1 divided by the resistance. It's 1 over the resistance. So if the resistance gets bigger, the conductance gets less. It's the material can't conduct as well. If the resistance drops, then it becomes a better conductor, and so the conductance goes up. Okay, and you know, it's we actually just swap these two over if we want to rearrange that equation. That's how we do it. Okay, so if we're told the conductance, we do 1 over conductance to find the resistance in ohms. Let's just remind ourselves of that. And or if we're told the resistance, we do 1 over that value, 1 divided by that value, and that tells us the conductance. Okay, if we're looking at a graph for those quantities, then if we had conductance here and resistance here, then we'd get a graph a bit like that. As the resistance gets bigger this way, then the conductance drops. But if the resistance reduces, going this way to 0, and then the conductance goes up. Okay. And that process just reminds me, with that equation Q equals IT, we can have a graph for that. Let's go back to that. Should have popped this in before. But again, if you had a circuit, and to be honest, imagine we had a variable resistor in there, so we could control the current, and then we measure the current. Well, actually, let's just put it through a bulb. Okay. Then, if we had a fixed amount of current in there, we'll measure the current with amps and ammeter. Then, as time goes on, if we measured the charge that flowed through that bulb, then we'd get a graph like that. So for 1 second, we might get a certain amount of charge. So let's say it was 10 coulombs of charge. After 2 seconds, we'd get twice the charge, 20 coulombs. Measure that in coulombs. 3 seconds, we get 30 coulombs of charge, etc. So that's a graphical relationship for how charge and current are related to each other. Okay. Next one. Okay, so just while we're talking about resistance, let's have a look at something called resistivity. Might have come across this at GCSE. We give it a little symbol. It looks like a P. It's a Greek letter called rho, but it looks like a P, and the unit is the ohm meter. So not ohms per meter, but just ohm meter. Ohm meters. Okay. And this is, again, it's a measure of how easily electrons can flow through something, but it's not dependent on the size or dimensions of the material. You might think a long wire has a higher resistance, short wire has a short resistance. This is purely dependent on the material itself, how it behaves. All right, so copper, silver, etc. has a low resistivity. And we probably think like plastics, wood has got a high resistivity. It's to do with the property of the material, not its shape. Okay, if we're looking at a formula, then we usually look at the formula this way. We can work out the resistance of a material if we know its resistivity. And if we're thinking of a wire, then we've got the cross-sectional area of the wire. We can work that out because area equals pi r squared, which also equals pi d squared over 4. So if we measure the diameter of the wire in meters, we square it, times it by pi, divided by 4. That would give us the area, cross-sectional area there, which is that A there. And then, of course, depending on the length of the wire, that's length, again, in meters. So these things have to, A is in meters, length is in meters, resistance is ohms, and we know that resistivity is ohm meters. A little bit busy, can't put it in there. Okay, so that's the formula, how that's related to each other. How might that look on a graph? Well, you could draw a couple of graphs, to be honest. If we're looking at resistance and length, if we go back to our formula, then remember resistivity isn't affected by length, it's only the resistance. So for a fixed resistivity, then R is proportional to L, so it looked like that. We also look at that formula, if we kept the same length but changed the cross-sectional area, then resistance would be inversely proportional to the area. So if we had a graph of resistance against area, we would see that it looks a bit like that. So that's a graph of an inverse relationship. Perhaps not so steep as that, but something like that. Yeah, that's fine. If we wanted to, we could then plot resistance against 1 over the area, and then we would get a straight line through 0, 0 for a fixed given resistivity. But these relationships relate to that equation. All right, next one. Let's have a look. So next one we might look at is energy in an electrical circuit. Okay, now energy, we sometimes use the word work. Work is really just the transfer of energy, but in this case it's electrical energy into something else. And so we give energy in an equation the symbol W because of work, because energy, another word for energy in science is work. We measure in joules. Okay, and the formula is this. We can work it out. We can't measure it directly, but we can measure the current. We can measure the voltage, and we can also time how long that circuit's been on. And we get this relationship here. W equals IVT. Okay. And we know what we've seen in the video. We know what current is in measured amps, V is volts or potential difference, and T is just time in seconds. Okay, we don't usually look at a graph really too much for that really. But if we wanted to, it would just be a very simple circuit. You can measure the current through a bulb. If we wanted context for that, we measure the potential difference across that bulb, and then, with whatever a stop clock looks like, we just time how long that circuit's run for, and we can work out how much energy by simply multiplying these three things together. If we get a question where we're trying to work out that, we just multiply those three things together, careful of the units, making sure time is in seconds. All right, rearranging it, if we wanted to make either subject, we just divide by V times T. So I, to get it cancels on this side, comes under here. If we want to work out V, very similar, we just divide by I and T. So W is always on top. Lastly, if we want to work out the time, we just divide both sides by I and V. Energy in joules divided by current times voltage. Okay. Next, let's have a look at power. So we define power as the rate of doing work. Okay, so it's basically power equals energy or work over time. You may know that we measure power in watts, which we give a capital W to as well. But in this case, if there's a number in front of that W, it's a unit for power. If the W is in a formula, then it's simply just energy. Okay, so energy is measured in joules, we know that, and time is in seconds. That's fine. All right, and so power is energy over time. If from the previous equation we knew that energy is IVT divided by time, you can see that the T's cancel. So power, if we just measure the current and the voltage, we can work out the power in that circuit. All right, so again, if we had our electrical circuit, give it a context, measure current, we've got a bulb with a certain power rating. If we measure the voltage and the current in that circuit, we just multiply I and V, and that tells us the power rating. Particularly useful if we've got an electrical circuit, a lighting circuit, and you know that you're going to have 100-watt bulbs in there. Well, we know the mains electricity, so P equals 100 watts. The mains electricity maybe equals 240 volts. So what kind of fuse system do we need? Well, we just take that formula, and we want to work out I, so we just divide both sides by V. So, V is power divided by, we want to work out the current. Divide both sides by V, 100 divided by 240, and just a rough idea, then that should give us about roughly about a quarter of an amp. Okay, so that might be the fuse rating we have as a result of that. So just an example how we use that formula and a little context for it. Okay, we're going to stay with power, but we're going to have a look at how we can use that formula even more. So P equals IV. If you remember, we had Ohm's law, or that equation for Ohm's law. We can, if we know the current and the resistance, but we don't know the voltage, we could work it out first, or we can just substitute it in for V. So can you see how we've got I there? And instead of V, I'm going to write IR. You can simplify that a little bit. I times I is just I squared and R. So again, you can use that formula to work out the power. If we wanted to rearrange that a little bit, so say we want to make I the subject, we would first of all divide both sides by R. So P over R equals I squared. We can put the unknown thing on the left-hand side. Okay, but of course we've got a square there, so to get rid of that, we square root both sides. That gets rid of the square root on this side, but I've got to square root this side as well. Just make sure you're square rooting the bottom part of the fraction as well as the top. So that divided by that, and then square root your final answer, and that will give you an answer in of course amps. Okay, just a variation on the original formula. Okay, now it's not required in our specification, but I'm just going to rearrange this formula to make I the subject, because it's a very popular formula as well for power at this level. Imagine what would happen if we substituted for I. So we put V over R instead of where that I is. What would that become? V over R, and then times that original V. So what does that become? That becomes V squared over R. P equals V squared over R. And so you know the potential difference. We square it, divided by the resistance in ohms. That tells us the power, in that circuit, dissipated in that circuit. And again, the most probably complicated one is if you want to find out what V is. Imagine you're told the power and the resistance. How do we work out V? Well, first of all, we multiply both sides by R. That would come up here and come up here. It would cancel on this side, leaving V squared on its own. But we still have to multiply. Oops, there we go. There, so power times resistance. And rightio, and then last thing, of course, we just need to square root both sides to get rid of that squared. So to work out the voltage, you multiply the power by the resistance, square root your answer, and that gives you an answer in volts. Another example of power in a circuit. All right, we're doing really well. Not far to go. Okay, let's have a quick look at series and parallel resistors. All right, and again, something we do probably in year 9, maybe year 8, depending on your school. So series resistors, R1, maybe R2, R3. Yep, so 3 resistor values in series. What's the formula look like for that? We simply, to find out the total resistance, so imagine we wanted to replace those 3 resistors with a single value resistor, then this is what it is. RT for maybe our total. We just simply add those 3 resistor values together. And if it was 4, you just add the 4th one, 5th, etc. Okay. Nice and tidy. All right, and then for parallel, it's a little bit more to it than that. Okay, so imagine you had 3 resistors in parallel. Okay, we'll call that R1, R2, R3. What would be the single resistor value for that? So the formula is a little bit more to it. So it's 1 over the total resistance, the single resistor. So that's what we're trying to do. We're trying to work out what's the equivalent resistor to these things. And it's 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3. And if there was a 4th resistor, yep, so whatever the values of the resistors in, you put them on the bottom. Okay, once you've got that value, you've got a equals whatever that is. Okay, you just put it in your calculator, it comes up with a value. Not sure what to give it the symbol, really, but it's okay. So let's just call it X then, because that's what we do in maths, don't we? We just put an X if we don't know the number. That's fine. So does that tell us what RT is? RT is that in ohms? No, it's not. It's 1 over the value of 1 over a value. All right, so to work that out, all I do is I swap them around. So I multiply both sides by RT and then divide both sides by X, and essentially they just swap places. So RT equals 1 over that X, and that will give us a value in ohms. Okay, where we have to be careful sometimes is that might be in kilo ohms, which is times 10 to the 3, for example, mega ohms, etc. All right, so you do need to include the kilo ohms in those bottom values when you're doing 1 over those values. Maybe use brackets in your calculators when you're doing that. All right, and so whatever that comes out to be, again, that would be the single resistor to replace those 3. Okay, series, you're adding them. Parallel, you have to do this. We call it the reciprocal 1 over values. Don't forget to do just to flip it and do 1 over that value at the end. It's typical where people forget to do that when in parallel. Okay, lastly, we're going to have a quick look at capacitors. So for capacitors, okay, we give it the symbol C for capacitance, but the unit is the farad, named after Michael Faraday. We give it a capital F. Okay, in capacitors, 1 farad would be a very big value, to be honest. So we usually use prefixes. Millifarads, you know, even that's quite big. So more typical is microfarads, which is 10 to the minus 6 farads. Nano. Yeah, let's go for nanofarads times 10 to the minus 9 farads. That's all it is. And picofarads times 10 to the minus 12 in some electronic circuits. Okay, so what is that? Well, essentially all it is if we have a circuit, and we might put a switch in there, and in this case, we'll just put a capacitor. Yep, that's fine. And we can measure the voltage across that capacitor. When we flick that switch, if we can measure the charge that's stored on that capacitor, we sort of charge up a capacitor. And essentially, if we plotted that on a graph, the amount of charge for the voltage from the power supply, if that was 6 volts, eventually you get 6 volts across here, for example. And what we find is that for 1 volt, we get a certain amount of charge, and 2 volts, we get a certain amount of charge, 3 volts, we get a certain amount of charge. We end up getting a straight line through 0, 0. And the gradient is the thing that we call the capacitance, is C. So you think C equals the change in Q over the change in V, or we sometimes write that formula as just Q equals VC. Yeah, if we wanted to work out the voltage, what would we do? We divide both sides by the capacitance. So the capacitance is the fixed value in the circuit, and the charge and the voltage are the things that may vary. So divide both. What do we do? Oh, divide both by C, so that'll be Q over C. If we want to work out the capacitance, it's Q over V. Or if we want to work out the charge, it's V times C. Okay. And sticking with capacitors, the last thing, we're going to just have a look at series and parallel. And easy to get this confused with resistors, but it's the other way. It's the other way around. The technique. All right. So if you have 3 capacitors connected together in series, what's the single capacitor value that would replace those 3? Well, this is the one that's 1 over. So it's 1 over CT equals 1 over C1, C1, C2, C3, plus 1 over C2 plus 1 over C3. What do? You work out that value. We're going to just call it X. So 1 over CT equals X. And of course, that's not the answer in farads. That's 1 over capacitance. So CT equals 1 over that X value. And that'll give you an answer in farads. Thing to look out for is if these values are in microfarads, is make sure you put the micro bit on the bottom so that the 10 to the minus 6 goes here. Okay, it's not 1 over, you know, if they were all 10 microfarads, it wouldn't be 1 over 10 plus 1 over 10 plus 1 over 10 and then put microfarads at the end. The microfarads bit has to go on the bottom, and that should be seen in the final value. The parallel one this time is the easier one, possibly mathematically, arguably, depending on what you like doing in maths. So what would be the single capacitor that's equivalent to all those? C1, C2, and C3. 1, 2, and 3. This is the easy one. Yeah, and that will give you, a final answer in farads. All right, so I hope that goes into some way to make you a little bit more familiar with how we do use some of the equations and formula in the specification for Unit 15 electrical circuits. And again, we've thrown in a few graphs in there too. Thanks for watching.